Okay, welcome. So what I'm going to do is, in today's class, I'm going to work out a very interesting problem that is called the spherical wrist. So in spherical wrist, what happens is uh, you have two distinct parts. The first part of the robot is used for position purposes, and the second part of the robot is used for the orientation purposes. So let me set up the problem. So the idea is, usually whenever you see a robot, you will have a 3 degree of freedom robot. So 9, 17, 20. 3 degree of freedom robot. It could be RRR or it could be RPP for the position of end effector. And you will have the last 3 degrees of freedom, DOF. It usually will be R perpendicular to R, perpendicular to R for the orientation. So what it means is you are going to have a robot arm that will take the end effector to the desired position, Px, Py, and Pz, and you will have a last 3 degree of freedom robot joint, which is RRR, that will take it to the desired orientation. Now, how do we solve the inverse kinematics problem for such a case? The idea is we solve these two problems separately. So this 3 degree of freedom RRR is called as spherical wrist. And I'm going to solve the spherical wrist problem first. So I just want to give you a very simple example. Think about it, that we have a robot arm which is shown something like this. I will draw a very simple kinematic diagram. So I have this robot arm. So I have this robot arm. Now this robot arm is actually an R robot arm. So you have this first R, second R, and the third R. So this is an R robot arm. And this, I'm going to call that end effector. The idea would be that I will have this end effector oriented and positioned at certain position. So what do I mean by position? The position means Px, Py, and Pz. But I want this end effector also to be oriented in a particular orientation, and usually we use Euler angles, roll, pitch, and yaw. A classic example is if you have a robot and you want that robot to be used for painting, then you need that paint can or paint gun to be oriented in particular orientation. So for an example, if you want to paint the ceiling, then you want to make sure that your paint gun is oriented in this orientation. And then you would have this robot arm, and this robot arm can actually go back and forth. Or if you want this painting to be done on the side, then you want to orient this end effector, and then you want to carry out the painting. To perform this particular operation, either it's painting, welding, or some other manipulation, this end effector, once again, needs to be oriented in a particular orientation in 3 dimensions. So what we do is, for that, we actually use something called as the spherical wrist. And this spherical wrist is something as simple as 3 revolute joints that are perpendicular to each other. And what I'm going to do is, I'm going to draw these 3 revolute joints. But please note that these revolute joints are perpendicular to each other. And I just want to show you a sort of a different configuration that will make it clear to visualize. So now imagine that this robot actually is a 6 degree of freedom robot, wherein you have the first 3 degrees of freedom responsible for position. So here, this robot dictates what should be Px, Py, and Pz. And imagine these last 3 joints, they are sort of on top of each other, which means the distance, the relative distance between them is negligible. So think about it like these 3 joints are on top of each other. So this is called as spherical wrist. And the sole purpose of spherical wrist is to orient the wrist in the orientation that we want. So you can add any different orientation. And just for a reference, in case if you don't know what roll, pitch, and yaw is, this terminology comes from the aircraft reference frame. So consider this is an aircraft. So this motion of the aircraft, this motion is called pitching. So this is pitch. This motion is called roll. And if you look at the center of the aircraft, this motion is called as yaw. So aircraft rolling means the one wing is going up and other wing is going down. That is rolling. Aircraft is pitching, which means the aircraft is taking off. Both the wings are going up. And aircraft is yawing, means the aircraft is turning. Now, again, one thing that is to be understood is pitching motion is about x-axis. So when I set up the axis for the aircraft, so this is the axis where you have the pitching motion. Yawing motion is about the z-axis. So this is x-axis, this is z-axis, and your roll motion is going to be about y-axis. So I want you to understand this. Roll is about y-axis, pitch is about x-axis, and yaw is about z-axis. And this roll, pitch, and yaw is called Euler angles. And usually when we look at robotics, they will say that the wrist orientation, roll, pitch, and yaw, they will give it to us. They will say the wrist is pitched by some amount, rolled by some amount, and yawed by some amount. And whenever roll, pitch, and yaw for the rest is defined, this is very important. Whenever, and I need to write this down, whenever roll, pitch, and yaw, RPY, for end effector are defined, they are with respect to Z0, X0, and Y0. So I need to write down this clearly. Roll is about Y0, pitch is about X0, and yaw is about Z0. So these angles, so if this is X0, if this is Z0, then clearly you have Y0 going like this. So the orientation of the end effector, this is the orientation of the end effector, is defined in terms of the axes that are fixed to the first joint or the zeroth frame. So what I'm going to do is I'm going to tackle this problem in two ways. First, I'm going to look at the spherical wrist. Before I begin, I just want you to visualize the spherical wrist. Spherical wrist, which means three revolute joints on top of each other, but they are perpendicular to each other, which means one revolute joint is responsible for the orientation about Y0. The other other wrist joint is responsible for the orientation about X0, and the last one is responsible for the orientation about Z0. And what I'm going to do is I want you for a second to look at this, something like this. You have this Z0. I want you to look at this axis. And please note, the last revolute joint will be parallel to Z0, which means theta 6 will control the orientation about Z0, that is nothing but yaw of the end effector. Now I want you to look at the second revolute joint, and this is the second revolute joint. What I'm going to do is I'm going to draw, first I'm going to draw axis, and then I'm going to highlight the axis. So second revolute joint is going to control its orientation. So I'm going to call this theta 6, or theta, this will be theta 5. So theta 5 will control the orientation about y. So which means in this orientation, y6 will control yaw. Theta 6 will control yaw. Theta 5 will control roll. And the last joint, which is this guy, it's parallel to x0. So theta 4 will control pitch. So I'm gonna remove this from here. So now please notice that the way I have drawn the spherical wrist, this spherical wrist can be used to orient the end effector in any roll, pitch, and yaw orientation. But the key question is, how do we find out those angles? So the question here is, how to find theta 6, theta 5, and theta 4 for any particular combination of roll, pitch, and yaw. So that is the problem we are going to attempt first. So let me solve this problem. So consider, and this is called as the inverse kinematics. Inverse kinematics of spherical wrist. Now, if you look at your homework problem, and if you have access to your the quiz problems, I want you to take a moment to look at the last quiz problem. In last quiz problem, which is problem number 5, I want you to identify the first 3 revolute joints. So can you see there is joint number 1, joint number 2, and joint number 3. So there are first 3 revolute joints, but at the end you have 4, 5, and 6. So problem 5, quiz 1, refer joint 4, 5, and 6. If you observe that figure closely, you will notice that these 3 joints are perpendicular to each other. So which means it forms some sort of a triad. So that is a spherical wrist. So the technique that I'm going to show you here is used to solve the spherical wrist problem. But for demonstration purposes, I'm going to separate out the joints by some distance. So let me draw the joints in the configuration that we are familiar. So what we have is, so this is my first joint. Then I'm going to have a second joint. And then I'm going to have a third joint. And then you have this end effector. Now please notice the way I have drawn this joint. You can look at your figure from the quiz. They are joint 4, 5, and 6. So this is joint number 4 in your quiz. This is joint number 5 in your quiz. This is joint number 6 in your quiz. But what I'm going to do is I'm going to start with a technique that we learned. So first and foremost, this is going to be my Z0, X0, Y0. Then I'm going to have Z1. Then I'm going to have Z2. I'm sorry, X2. And then I'm going to have Y1. So this is Z1. This is going to be my Z2. This is going to be X2. And this is going to be my Y2. And the last but not least, this is end effector frame. And I'm going to draw this exactly similar to C3, X3, and Y3. Okay, so just make sure that we satisfy all the 4 rules when we drew this. And one thing I want you to understand, that even though I have drawn some physical distance between this joint, so you may say this is A1, you may say this is A2, and you can say that this may be A3, But since we are trying to solve the spherical wrist, the assumption is A1 is equal to A2 is equal to A3 is equal to 0. So these joints, three revolute joints, are sort of on top of each other. And with this, I'm able to solve the orientation problem. And this is actually a simple orientation problem. So what I'm going to do is I'm going to assume my theta 1 to be like this. I'm going to assume theta 2 be like this. And then I'm going to assume my theta 3 to be like this. So I have drawn the kinematic diagram for the spherical wrist. And before I proceed any further, I just want to ask you, are there any questions regarding this kinematic diagram? I'm looking at the chat window. Everyone understood the kinematic diagram? Now I'm going to start with my first joint, which is 0, R1. And this 0, R1 joint is cosine theta 1 minus sine theta 1, sine theta 1, cosine theta 1, 0, 0, 0, 0, 1. This needs to be multiplied by the projection matrix. And the projection matrix is x1, y1, z1, x0, y0, z0. Now check this out. The projection of y1 on z0 is 1. Projection of x1 is 1. And projection of z1 is minus 1 on y0. So when I perform this multiplication, I should be able to formulate the homogeneous transformation matrix. So my 0h1 is going to look like first row, first column, cosine theta 1, first row, second column, first row, third column, second row, first column, second row, second column, second row, third column, third row, first column, third row, second column, third row, third column, finally 0, 0, 0, and 1. And I'm writing this so that we are on the same consistent page. Please notice, since A1, A2, and A3s are 0, technically I'm supposed to write A1 over here, but it's a spherical wrist, and spherical wrist, which means all the distances are 0. So I'm going to write down 0, 0, 0. Everyone with me so far? So I found out my first homogeneous transformation matrix for the spherical wrist. Now I'm going to write my second homogeneous transformation matrix, which is 1, R2. And 1, R2 can be written as cosine theta 2 minus sine theta 2, sine theta 2, cosine theta 2, 0, 0, 0, 0, 1. Let's not forget the projection matrix. And the projection matrix happens to be x2, y2, z2, x1, y1, z1. So let's look at x2. x2 is in the orientation of y1, 1, 0, 0. y2 is in the orientation of z1, and z2 is in the orientation of x1. So 1, 0, 0. That allows me to find the second homogeneous transformation matrix, and I'm going to write that down directly, which is 1, H2. And this is going to be again a 4 by 4 matrix. First row, first column, that gives me minus sine theta 2. First row, second column, that gives me 0. First row, third column, that gives me cosine theta 2. Second row, first column, cosine theta 2. Second row, second column, 0. Second row, third column, sine theta 2. Third row, first column, 0. Third row, second column, 1. Third row, third column, 0. Again, 0, 0, 0. I'm going to have 1 here. And ideally, I should be having A2 cosine theta 2 and A2 sine theta 2 as the distances y1 and x1. But since this is a spherical wrist, my distances are 0. So I'm going to add zeros. Any question here? Now the last homogeneous transformation matrix, it's very easy because last homogeneous transformation matrix is 2R3. And this 2R3, please note, is cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, multiplied by the projection matrix. And I want you to note the projection matrix here is x3, y3, z3, x2, y2, z2. But check this out. X3, Y3, and Z3 is aligned with X2, Y2, and Z2. So it's just gonna be 0, 1, 1, 0, 0, 0, 0, 1, 1. Which means my homogeneous transformation matrix will be, and I'm gonna write it down on the next page, is going to be 2H3 is equal to cosine theta 3 minus sine theta 3, 0, sine theta 3, cosine theta 3, 0, 0, 0, 1, 0, 0, 0. And ideally, I should have the distances here. But since it's a spherical wrist, I'm going to have 0, 0, 0, and I will have 1 over here. Everyone understood this? Finally, I'm interested in 0H3, which is 0H1, 1H2, and 2H3. And this multiplication, I would like to find out using MATLAB. So if you are with me, I would strongly recommend that you start up your MATLAB. So open up a new script, and I'm going to call this IK of spherical wrist. Can everyone see my MATLAB? Spherical wrist. So I will start with SYMS, T1 for theta 1, T2 for theta 2, T3 for theta 3, 0H1 is going to be cosine T1, 0, sine T1, 0, sine T1, 0, minus cosine T1, 0, 0, 1, 0, 0, 0, 0, 0, 1. This is my H01. H02 is equal to minus sine T2 0 cosine T2 0 cosine T2 I saw some thing in chat. I just need to check quickly what was the comment on the chat. So I don't see any comment in the chat window. Yeah, okay, good. Yeah. H02. Oh, H12. Yeah, H12. Okay, cosine T2, then 0 sine T2 0. Next one is 0 1 0 0 0 0 0 1. Then the last one is H23, which is cosine T3 minus sine T3 0 0 sine T3 cosine T3 0 0 0. I made a mistake here. Okay, H23 should be here. Cosine semicolon 0 1 0 0 0 0 0 1. So that is how my matrix looks like. Uh, did I think I made a mistake. I deleted H12. H12 is minus sine T2 0 cosine T2 0 cosine T2 0 sine T2 0. Then I have 0 1 0 0, and then I have 0 0 0 1. Okay, let me see if I made any mistake here. So obviously this needs to be capital. So SYMS T1 T2 T3 H01, and check my H01 if it is same as what we derived, and it looks okay to me. H12 is sine cosine sine 0 1, and H23 cosine sine and cosine. Okay, so now we have H01, H12, H23. So what I'm going to do now is simplify H01 multiplied by H12 multiplied by H23. And so now I want you to notice this long answer that we got. So now, but I want you to sort of carefully look at what we have here is we have sine T1, sine T3, cosine T1, cosine T3, sine T2, cosine T1, cosine T2. So what I have here is I have a combination of various terms. So somehow I need to solve this matrix to find out the values of T1, T2, and T3. So I have the homogeneous transformation matrices. From the homogeneous transformation matrices, I have the product. So this is the first homogeneous transformation matrix. This is the second homogeneous transformation matrix. And finally, I have this third homogeneous transformation matrix. Please notice last column are a bunch of zeros. And the reason they are a bunch of zeros because the positions are not in there. So the matrix that I am interested in is nothing but the first 3 by, actually I made a mistake in the H23. I don't know if you noticed this. H23 is 0, 1. I made a mistake in H23. This cannot be at this location. It should be at this location. So now, okay. Let's see, did I make dimensional mismatch somewhere? 0, 0, 1, 1, 2, 3, yeah. So this has to be cosine. So H23, the first element is correct. The second element needs to have 2 zeros. H23. The third element is 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 1, 0, and 0, 0, 0, 1. So H23, I actually made a mistake and now I have corrected it. So let's see H01. So H01 looks okay to me. H12 looks okay to me. H23, let's see, H23 looks okay to me this time. Sorry about that. Now the last one is simplify. And now I land up with this big expression. So I just want to check with students who are online if they were able to get the same answer. Okay. I see already students caught my mistake in the online chat, but once again, is it correct now? Yes, Ima, Andrew, John, Asjad, everyone. Okay. Okay. Now, finally, I got this matrix correct. Now, somehow, what I need to do is I need to solve some equations. And I will start with something very simple. So what is given to me? So what is given to me? Given. I'm given certain roll angle certain pitch angle and certain yaw angle. So I'm gonna write, given my roll angle is say pi by 2, my pitch angle, and this could be anything, okay, my pitch angle is pi by 3, and the reason it's in pi by 2, pi by 3, because MATLAB requires the angles to be in radians, and my yaw is maybe pi by 6. So this is the final wrist orientation. This is the end. So this is the end effector orientation. Given EE orientation, find T1, T2, and T3. Everybody understood this is the spherical wrist problem. Yeah, of course. You can use cosine D and the angles would be, but just a second. Because what I'm going to do is, these are Euler angles. And somehow I cannot compare dollars to pesos. So I need everything to be in same consistent unit. So what I'm going to do is, and listen to me very carefully, I'm going to take this roll, pitch, and yaw, the orientation, and convert that into a rotation matrix. Now, please notice that first 3 by 3 is my rotation matrix. So what I have is my rotation matrix is something like this. My R, I'm going to say REE is equal to copy, paste. Then I have second row, copy, paste. Where did it go? Okay, paste. And the last one is, so before you convert this into degrees, just hear me out. So the last one is this. So now I have this rotation matrix. So this is just the rotation matrix. So this is the rotation matrix. Now the question is, given the end effector orientation, I'm going to find out the rotation, actual rotation matrix. I'm going to say R. And the command to find the R from the roll, pitch, and yaw is simple MATLAB command, Euler to rotation matrix. So EUL to ROTM. This is the command that we will use. EUL to ROTM. So this will take the Euler angles in radians and convert that into a rotation matrix. And there is a specific way this needs to be defined. And I'm going to write this down because you may use it a lot. EUL to ROTM, and in the parentheses you need to provide roll, pitch, and yaw in this sequence, because there are 12 ways Euler angles can be defined, the way the sequence of orientation works. But for robotics purposes, we will always use the combination roll, pitch, and yaw. So whenever you use MATLAB command, you will have to supply roll angle first, pitch angle second, and yaw angle third. So what I'm going to do is I'm going to say EUL to ROTM, parentheses, add square bracket, roll is pi by 2, pitch is pi by 3, and yaw is pi by 6. So roll is pi by 2, pitch is pi by 3, and yaw is pi by 6. And then parentheses complete. And I want you to see what happens now. So when I evaluate this matrix, I have these two matrices. I have REE and I have R. Can you see this R is nothing but a completely numeric matrix, which means now I can compare term by terms. I give you a very simple idea. Check this out. I want you to look at the last term. Can you see this term is just sine T2? And I want you to look at the last term in R. Can you see this term is 433, which means I can say my T2 is equal to A sine arc sine 0.433. That gives me the value of T2. So let's evaluate this. And then once I evaluate, guess what? My T2 is 0.44. Now check this out. Next term is here. This term is similar to this term. So which means the equation is 0.25 is equal to minus of cosine T2 multiplied by sine T3. And I'm going to write this equation down just for the reference. Cosine T2 multiplied by sine T3 is equal to 0.25. Now please note, we know the value of T2. So what I'm going to do is T3 is equal to A sine in the parentheses 0.25 minus, it will 0.25 minus cosine of T2 that we already found. So, and then evaluate this. I got T3. Now the last but not least is I need to find T1. So let's find the equation. Can you see the first equation that has sine T1, sine T3? So I'm gonna, oh yeah. It's divided. Correct. So, okay, 0.28. Now, what I want you to do is, I want you, question? Do you have a question? So, the last thing I want you to note is somehow I need to find a term where the T1 is present. And guess I have this term over here. So, if you look at this equation, it's cosine T2 multiplied by sine T1 is equal to 0.75. So what I'm going to do is A sine, so T1 is equal to A sine 0.75 divided by cosine of T2. And there is one more parentheses missing. And I got the values of T1. Yeah, so this is how you would solve inverse kinematics problem. So I will clear all CLC, and those T1, T2, T3s are in radians. That's why I told you not to use degrees in initial stuff. So now you have T1, T2, and T3, and these angles are in radians. So that's why I don't use cos D or sine D when you substitute in the rotation matrix or in Euler to rot, because I think Euler to rot command requires the angles to be in radians. Okay, everyone understood this problem? So this is how you would solve the spherical wrist. Expand the editor window. Yes. Do you want me to make it a little bit bigger? Have an error for EU12 rotor. Yeah, I mean, usually when you install MATLAB, I recommend that you install with all the default options and the toolboxes that we need for solving robotics problem. So yeah, EUL, yeah, correct. It's not EU12, it's EUL. That stands for Euler to rotation matrix. Okay, any questions? Now I want to discuss a complete robot, and clearly I won't have time to discuss. If the angles are not given in radians, you should convert those in radians. Okay, now I'm gonna go back to my PowerPoint. So, but before I do that transition, I just want to make sure that you are able to get the code and understand what I have done. No, that is something you want to be careful about. ZYX is the Euler angle sequence. But for that Euler angle sequence, you would want to specify the angles roll, pitch, and yaw. And if you really want to go in the details of that, MATLAB has a very nice help where they explain the coordinate system in robotics. My R output is this. So please note this ZYX, this coordinate system, even though it is specified by ZYX, it is not yaw, roll, and pitch. It has to be roll, pitch, and yaw. So what I'm going to do is I will try to show you what that means. And I'm gonna go to Zoom and switch my window. So look at this help, coordinate system in robotics. In coordinate system in robotics, I want you to note that the default orientation is something like this. So it is always, this is denoted as RPY. Oh, okay. Yeah. I have to be very clear about it. The way we are defining the roll, pitch, and yaw, our roll is about y-axis, our pitch is about x-axis, and about our yaw is about z-axis. So the way MATLAB is referring to them is different. So what I want you to make sure, so I think when you have rotation matrix gxy, your row to this should be, since this is z xy, I would put it like yaw, pitch, and roll as per our sign convention. So our sign convention is z is yaw, y is roll, and x is pitch. Okay. You are supposed to see MATLAB, and yes, what I will do is now I will go to, once again, stop screen, share screen. This is what you should see. So please make a note. This should be Z, X, and Y. So this is how it should be. So I made a mistake here and I will go ahead and correct it. So my roll is pi by 2. So since my roll is pi by 2, this is gonna be like this. My pitch is pi by 3. So this is pi by 3. And my yaw is pi by 6. So this is how it would look like. And then this is I'm gonna evaluate. So when I evaluate this, I get this matrix, and I have this REE. So you will have to compare those values. So just for my own satisfaction, I will work out this problem again. So that you have the right solution. I made a mistake in supplying the angles. It needs to be the way the MATLAB is asking is ZXY. And since our sign convention Z is yaw, Y is roll, and X is pitch, so I need to supply the angles as yaw, pitch, and roll. So this is how I should be supplying. And now I get these angles, and now I have cosine sine T2 is 0, which means the first angle is going to be 0. So sine, so this is 0. The second angle, I should be sharing I should be sharing MATLAB. You should be seeing MATLAB. You're not? Does MATLAB help says ZYX? Okay, let me see. Just what is it? Z. There are. I'm just using the default one, which is okay. Z. Oh, I see. Oh. I don't know if you have noticed this. There is an issue with MATLAB help. This is ZY. Okay, and I will. I'll show it to you. Okay, can you see there is a typo in the MATLAB? So the MATLAB rotates. It supports two rotations. One is ZYZ order that is commonly used in robotics, and the other one is XYZ order, which is also denoted as roll pitch Y. So we are actually using ZYX. So please note there is a typo in the MATLAB. It's not ZYZ. So, and to be more specific, to force MATLAB to use the sign convention that we are using, what I'm going to do is I'm going to specify ZYX. So the way we are doing it is ZXY. So I can say ZYX. So Z is yaw. And then I will substitute here ZYX. So this will become Z. So this should become yaw pi by 6. This is roll. So this should become pi by 2, and this should become pi by 3. And please note this command. So I will repeat this. Okay, so SYMS, valid selection. Then you have re, and then you have this. So let's see what MATLAB says. C. So I don't know if this needs to be capital. ZYX. Okay. So help EUL to ROTM. Okay, I forgot to add the parentheses. So we are not using ZYZ, we are using ZYX. Okay, now this makes sense. So I got this ZYX, and now you should compare the terms. And the comparison of terms, when you compare, you will be able to find out the values. So let me see REE. Okay, so sine T2 is 0. T1 is cosine T2. So that value is cosine T2 is minus 0.5. So this becomes minus 0.5, and T1 is 0.866. So, and this solution should be correct. So I just want to clarify the mistake I made earlier. The default MATLAB does not use the coordinate system that is used in robotics. Robotics, there are 12 combinations of Euler angles. Out of that, in robotics, we usually use ZYX Euler combination. So whenever you are going to convert given Euler angles to the rotation matrices, as you have seen from my mistake, depending upon what order of rotation you specify, your rotation matrix is going to be different. So the way we are going to specify is ZYX, where the Z is the rotation, and with our convention, the rotation yaw is about Z. Roll rotation, the angular rotation about Y is called roll, and angular rotation about X is called pitch. So Euler to rotate, the first element has to be the rotation about Z, which is yaw. Second rotation is about Y, which is roll, and the third rotation is about pitch. So I need to make correction here. Z, roll, and pitch. Okay, so make this correction, and then you should be able to solve the spherical wrist problem using mathematics. And I'm going to look at the chat window. Should T3 capital in single quote? Should T3 use 0? Did I still make mistake? Finally, it's T2. I didn't understand John's comment. Shouldn't T3 use 0? So let me see. I have cosine T2 by T3. T3. So T3. Yeah, it's EUL, not EU12. Okay, so shouldn't T3 is equal to A sine T3. Oh, so T3 is, so so first and foremost, I'm using the last equation to find T2. Then I am interested in finding out T3, which is, I'm using this equation. I can use this equation, or I can use this equation. And then, yeah, so probably just compare sine T2 from here to find T2. Then I need to use T2 and T3. So I can use either this equation or this equation. So I use cosine T2 sine T1, cosine T2 sine T1. So sine T1 is 0, Okay, so you mean oh, it is not equation, the number that I have used. Look in the, okay, okay, yeah, yeah, yeah. Okay, okay, all right. And T1 is okay, right? So idea is you compare term by terms and then find out the values of T1, T2, and T3. So that is how you will solve a spherical wrist. And if you look at the last problem, problem 5, it has first 3 revolute joints. R is perpendicular to R, parallel to R. And what you need to do is you need to solve these two separately to come up with the position solution. So what you will do is you will find theta 1, theta 2, and theta 3 such a way that you will achieve the position Px, Py, Pz, and then you will find out theta 4, theta 5, and theta 6. So, oh wow, now John changed his mind. Okay, all right. It's becoming a little complex for me to keep track of, but I know that you kind of understood what I'm trying to do is I'm comparing apples to apples and bananas to bananas. So compare those and find out the angles. Okay, with this, I'm gonna stop here, but if you have any questions, I would be happy to answer. And if you still want me to work out this problem from the beginning, I would be more than happy to do it uh, in next part. So first we have H01, H12, H23. We have this matrix. So clear all. Okay. Now I need to pick up the equations and I will go again step by step. Sine T2 is 0. So what this means is T2 is A sine 2. Then what I need to do is I need to use a second term. I can use any term. That's totally fine. I can do cosine T2 and cosine T1, cosine T2 and cosine T1. So I can do cosine. So first I have cosine T1 and cosine T1 and cosine T2 is equal to 0.866. So what this means is 0.866 divided by cosine T2 is gonna give me cosine T1. So I will have A cos, and the last term is gonna give, this is gonna give me T1, and the last one I need to find out value of T3, and for value of T3 I'm going to choose this equation minus cosine T2 plus multiplied by sine T3 is equal to 0. So what that means is T3 is equal to arc sine 0 divided by A cosine T, so cosine T2. Okay. Okay, now this is the answer I finally got. My T2 is equal to 0, my T3 is equal to 0, and my T1 is 0.52. Now, the other folks who have already worked out the problem can tell me if my answer matches with your answer. And if not, I will go ahead and upload this MATLAB script, and then you can look at the way I have calculated the angles. Calculation of homogeneous matrix of end effector. So calculation of the homogeneous transformation matrix in the end effector. So end effector has two things. End effector has certain positions and end effector has certain orientations. End effector orientations are input to the spherical wrist problem, and end effector positions are input to the inverse kinematics of the first three joints. So that is how you will solve an inverse kinematics. So actually, I will try to work out one more problem next class, wherein we do the whole thing for a 6 degree of freedom robot arm. That way it will be clear how to separate out the positions part of it and the orientation part of it. Well, large picture, at this particular orientation, only one angle, one orientation is required. But in some other orientation, all three angles could be required. So that is the reason why, I mean, in this particular orientation, roll, pitch, and yaw, it turned out that by just turning one angle and by keeping the other angles 0, we were able to get the required orientation, but it may not happen all the time. You could potentially get very nasty homogeneous transformation matrices. Yes, you could get quite bad homogeneous transformation matrices, but please understand the homogeneous transformation matrix for spherical wrist does not change. Once again, the homogeneous transformation matrix for spherical wrist, which is nothing but REE, does not change, because that is the way we perform the calculations. The orientation, the homogeneous transformation matrix for the joints that are before spherical wrist, that could get nasty, but that is something which is similar to the 3 degree of robot arm that we have solved so many times. Okay, are there any other questions? So yes, so the final answer is going to be, you will have the homogeneous transformation corresponding to first three joints multiplied by the homogeneous transformation corresponding to last three joints. That is the final homogeneous transformation. But when you want to solve it, you basically solve it in two distinct steps. All the lectures will be uploaded in Canvas. So you will do it in two distinct steps. So you will use 0H3 to find positions and 3H6 to find orientation. And I understand, I'll work out a problem again, step by step. But before I go, please note, I just want to repeat the mistake I made in today's class. Euler to root M, we have to use the coordinate system that is conventionally used in robotics, which is Z is yaw, Y is roll, and X is pitch. And your input to Euler to root M will be yaw, roll, and pitch. And don't forget to specify the orientation angle, which is z, x, z, y, and x. Because as you know that if you use the default z, y, z, then your answers are going to be incorrect. And I'm gonna just, for everyone's understanding, I'm gonna send a link to where in MATLAB, MathWorks help that shows the subtlety in this transformation. There are 12 combinations of Euler angles. So please use the right combination to get the right angle, right angles. Make sure you click that if you want it. Okay. Oh, so the robotics toolbox, scroll down to T1. Scroll down to T1. So robotics toolbox, actually here is the issue with robotics toolbox. Some coordinate systems are different. The robotics toolbox that was developed by the professor, that I think there are some coordinate systems that are different. So your answers would be the same, but the signs won't match. So you are welcome to explore robotics toolbox, but be careful with the sign conventions and the functions, the way they are used. Okay, where it is, can you scroll down to T1? I'll go down to T1. You mean like this? So just for, I will also add it over here. Okay, I'm gonna stop recording.